Hello everyone and welcome to lecture today. So today what I want to do is discuss two different very neat, very cool applications of the integral theorems that we've been looking at. These are specifically the applications of the Divergence Theorem and applications of Stokes' Theorem. We actually have many different possible applications. Today I'm going to be focusing on applications coming from physics and engineering, namely the heat equation, which is also sometimes called the diffusion equation. So what I want to do is start by discussing how to derive the heat equation. This is a partial differential equation that governs the temperature distribution throughout a given medium in any number of spatial dimensions as a function of position in a given region and time as well. So it basically governs how heat flows through objects. And in general, you can consider this equation in any number of dimensions, but we're going to stick to first looking at what equation we get in 3 dimensions and then kind of reduce that down to 2 dimensions and 1 dimension. There are a number of different ways of deriving this equation in general, but I very much like this method because it kind of starts from the big picture and moves down to the small picture, and you really see how the heat equation is defined and what it's saying about a given region. And so before getting into any calculations or the derivation, what I want to do is going to give you a motivating thought. Suppose you have a temperature distribution in 2D, so a 2-dimensional plate, say, where the middle of the plate has a temperature of 1 and the other portion of the plate has a temperature of 0. So in this case, the red square here on the right has a temperature of 1, and the blue portion of this region has a temperature of 0. On the left is just a graph of this function in 2D. Or you see the graph of the function has the value of 1 on the red square, and it has a value of 0 off of the red square. What we want to do is derive an equation, a partial differential equation that governs how this temperature is going to flow if we just kind of let time go. And this is kind of a thought that I want to leave you with right now. But at the end of the video, I will show what the exact mathematical solution to this equation that we're going to get looks like in 2D. By the end of the course, we'll actually see how to solve this. So let's say we have this 3-dimensional region of Euclidean space, omega. And omega is the volume of the region, so the inside of this region. In the surface of this region, or the boundary of omega, I'll call S. And the idea here is that what we're going to be looking at specifically, we're going to assume that there's some sort of temperature distribution. So say maybe regions of hot, regions of cold, is that initial temperature distribution, and then all temperatures kind of in between inside this region. It's really kind of like is a fairly standard scenario. And we want to say, well, we know the temperature is going to be kind of different at every given point here, in general, the temperature is going to be given by some function, we'll call it u, at a point r and a time t. So we're going to have some initial temperature, well, u naught of r, which is a given function, and it's equal to the temperature function at t equals 0. And a little bit later on in the course, we're actually going to see how to solve the heat equation. But for now, what I want to do is just go over the derivation of the heat equation using vector calculus. So it kind of ties together a lot of the stuff that we've been talking about. And so the main idea here that we need to kind of wrap our heads around is the idea of heat flux. And specifically, we're going to say that the heat flux vector field is going to somehow depend on u, right? And we need to kind of use some knowledge about vector calculus and how functions behave to really kind of argue about what form the heat flux vector should take. And so the question is, how can we determine this? And it turns out that this can be determined pretty nicely using what's called Fourier's law. And this is actually something you've seen in 1D if you've ever, say in your differential equations class, seen Newton's law of cooling. So I encourage you to look that up. And Newton's law of cooling is also found using essentially what we're about to do in 1D. But specifically, what we're going to do is use something called Fourier's law. And essentially what this is looking at, and what this is saying, is that the temperature scalar field, because temperature is a scalar function of position and time, so it's a scalar field. This temperature field has to obey certain properties from calculus and also certain physical properties that make sense. The main two properties that we're using here, I'll say the properties from multivariable calculus, and specifically I should say these are properties of the gradient of U. We know that the gradient field is always going to point in the direction of fastest increase in the function u. So this is one of the things that we're going to be using. The other thing that we want to note is that temperature at any point should be flowing opposite to the gradient of u. Right? And these are the two basic things that we're going to be using when we write down Fourier's law. This makes a lot of physical sense because it's essentially saying this second kind of property that we're using here is a property from physics. This is a property of gradient of u. And the idea here is that it makes a lot of sense if you just kind of think about how temperature typically behaves, right? Temperature will always flow from hot to cold, which means that if the gradient of u at any point points in the direction of fastest increase in temperature, the temperature is going to flow in the direct opposite direction to this vector at any point in the medium. So, sure enough, these are two kind of assumptions and properties that we're using when we write down Fourier's law. So what we're going to say is that the heat flux vector field, which gives the flow of heat energy at any given point, sometimes also called the flux density, and it's denoted in a wide variety of notations, but we'll just call it phi q. It's a vector field, the vector function of position and time. This at every point in space and in time should be proportional to negative times the gradient of u, or negative some constant k times the gradient of u. Right, this is a vector field, and it's basically saying that heat energy should flow opposite the direction of the gradient vector, because the gradient vector always points at fastest increase in temperature, and therefore the heat should always flow in this direction, or opposite to the direction of the gradient at any point. For any surface S that's nice enough, also this vector field has to be nice enough to apply the divergence theorem, but we can sort of find an accumulation of flux of heat energy through the surface by taking the surface integral of this vector field. So the total amount of heat flux through the surface S, which is the boundary of some region omega, is going to be equal to the surface integral over the surface S of the heat flux vector, or vector field, dot product with n hat, where n hat is just the unit normal vector field to the surface. So right, and this is directly consistent with the way that we've defined fluxes of vector fields through surfaces. So this quantity that you get when you calculate this surface integral gives you the total amount of heat energy that flows out of a surface, surface S. So before moving on to a little bit more of the math, what I want to do is discuss some of the physics, specifically the units of this heat flux, and what the actual units of the thermal flux are, because I think that makes things just a little bit more understandable. So if the heat flux value, the value of heat flux on this through the surface S, is equal to this double integral right here, n hat is a unit vector. It doesn't have units. ds, right, is going to correspond to, because this is an area integral or a surface area integral, you're always going to pick up units of area with this ds right here. And then that means that this value, the value of this vector, has to be measured in something that will give us units of a heat flux. And a heat flux is really a rate of energy change through the surface with respect to time. Right? This is the idea of flux. So the units of this vector field are, generally speaking, going to be a rate of energy change with respect to time. And this is the flux vector. When we integrate the surface integral here, this needs to be over units of area. In SI units, this is specifically given by the rate of energy change with respect to time, is called the watt. So WATTS per meter squared, units of area. This is a dimensionally consistent idea. This breaks down even further. A watt is a joule per second. So in SI, you could also say that, this is joules per second over meters squared. But this is the idea of what this vector field is being measured in. In general, it has to be a rate of energy with respect to time over units of area. And so this value of heat flux is going to have units of just rate of change of energy through the surface at any given time t. And this is going to justify some of the steps that we're going to take a little bit further on. But with Fourier's law, this is the same thing as the surface integral of kappa gradient u dot product with n hat ds. This is by Fourier's law. And so the idea then also, I do want to kind of clarify here, k in general does not have to be constant. Okay? K is called the thermal conductivity of the material that we're dealing with. And in general is a function of position and possibly time as well. And most generally, K could actually be a matrix, right? If you have what's called an anisotropic material, you will have that K is actually a matrix function of position and time that's multiplying the gradient vector. We won't be considering that right now because it's a little bit more complicated, but the equations that you get are similar and still do apply to really more interesting problems in mechanics and heat flow. So the idea here is that in general we want to think of K as a function of position and time when we're deriving this, because this is how we get the most general differential equations that govern the heat flow in the medium. And so you might also be wondering what the units of this K are. And everything has to be dimensionally consistent always when we're applying mathematics to the real world. So the units of the thermal conductivity function this equation has to give you the units of the heat flux, phi q, and phi q is a rate of energy change with respect to time per unit area. The units of U are temperature, which in SI, or standard units, are measured in Kelvin, or is measured in Kelvin. So the units of the gradient of U, which is all of the collection of partial derivatives of temperature with respect to space, are going to be measured in temperature over distance. Because whenever you take the derivative of a quantity, you get 1 over the distance, the first derivative, which is a neat thing to show. So I recommend you go through and do that. Or in SI, this would be degrees Kelvin per meter. So the units of this thermal conductivity have to end up being rate of energy change with respect to time over a unit of area. So this expression has to be a rate of energy change, or have units of the rate of energy change, rate of energy with respect to time, over length times temperature. Or in SI, watts per meters Kelvin. So these things are not necessary for what we're about to do because you can do what's called non-dimensionalize all equations in applied mathematics. But I do like going over this because I think it brings some real world feel into what it is that we're doing here. Specifically the units for heat flux being the energy per unit time. You remember that we can, one of the abbreviations that I'll sometimes use for flux is capital phi S. This is the heat flux through the surface S. So basically what we have here is that assuming that we look at a small interval, a very small interval, delta t, and these functions are nice enough functions, so all of these vector fields are nice enough, we get that the total energy flowing through the surface S in the time interval delta t is going to be approximately equal to the heat flux through S multiplied by this time interval delta t. And the reason this is working, this is a good approximation, is because for small delta t is, you can think of the heat flux, phi s, as the partial derivative of the total energy change with respect to time, right, flowing through the surface S. And this is going to be really important because this is going to essentially combine with the what's going on inside of the medium as well. So far, we've only considered stuff on the boundary of the medium, right? So the total amount of energy flowing through the boundary of this region S. Now, so given this, right, we want to try and connect this to what's going on inside the boundary as well. Because if heat flows out of the boundary through this surface S, then we also have to kind of think of what's going on inside the boundary as well. And one of the big assumptions that I'm going to make here is that there are no sources or sinks, so no places where we're producing heat or using up heat inside of the three-dimensional domain omega. These sources or sinks would occur, say, if there's a chemical reaction going on inside the region omega, which is could be producing, right, or using up some sort of energy, or, for instance, radioactive decay going on inside omega, which would be decaying energy at points inside the region omega. These things can be dealt with. And they do give more interesting, more realistic models. But for now, we're just going to stick with the simplest possible case we can think of, which is going to be no production or usage of energy inside of the region omega, just to simplify things. But anyway, so we know that the temperature U is changing with respect to time at every given point. So the partial derivative of a U with respect to T is the rate of change of temperature with respect to time at every given point T. And if this is happening at every given point, what we want to do is we want to consider, in some sense, the triple integral of this. We want to think of this as a density function. And specifically, we want to get something that directly matches up with what we have right here in terms of the units. So we consider two more, new functions that are actually very physical functions. The mass density of the medium, which is going to be related to anytime you have a triple integral of a density, you're going to have to consider the mass density and what's called the specific heat of the medium at every given point. These are two physical properties that we need to kind of factor in and tie into this model. So these are given by a variety of different notations, but typically rho of r, so rho of position, and possibly also of time, but we're just going to consider not changing mass density of time, so rho of r. This is the mass density at every point. And the specific heat, mu of r. And just like before, I want to do a dimensional analysis and show you the units of these so you're not confused by what's going on here. So the units of the mass density are pretty straightforward. The mass density here is a volumetric mass density, so this is going to be mass over volume, or length cubed. In SI, typically this is given by kilograms per meter cubed. Specific heat or specific heat capacity is something that you might not be as familiar with, but essentially, informally, this is the amount of heat that must be added to 1 unit of mass of a substance in order to cause an increase of 1 unit in temperature. In order to make everything work out correctly, this is measured in units of energy over temperature times mass. Or in SI units, joules per degrees Kelvin per kilogram. And so because each of these things we can in some sense think of as a density, even the partial derivative, partial u, partial t, right? This is measured in units of temperature over time, or in SI degrees Kelvin per second. And each one of these things we want to think of as a density in some sense. Well, when we multiply these three quantities together, mu times rho times the rate of change of u with respect to time. This is mu right here. This quantity right here is going to have units of energy over length cubed, so volume times time. Or in SI, this will be joules over L cubed times, or M cubed, meters cubed times seconds. which if we rewrite a little bit, remember that joules over second is the same thing as watts over, well, joules over second is the same thing as watts, so this is the same thing as watts over meters cubed. So really this is this quantity right here you can think of as a volumetric density, specifically at every given point. This is the volumetric flux of energy. And specifically it's the flux density, the volumetric density. Because specifically, you can think of it, every single point here, this is giving you at that point the flux density for the energy. And this is a really, really important point to kind of consider. So the idea is that using the triple integral then, if this is a density, we know that the total amount of flux through the volume of this this quantity is going to be the triple integral of this quantity. So the volumetric flux of energy through the volume omega is going to be the triple integral of this density function over the domain omega. And so this quantity, right, the volumetric flux of energy through the region omega, is going to have units of just watts. Which means that, just like before, if we consider a small change, delta t, the change in total energy is going to be approximately equal to this total volumetric flux times delta t. So this means, just like before, this expression right here is really, we think of it as the derivative with respect to energy, rate of change of energy inside of the region omega. So the volumetric energy inside the region omega, this quantity is like the rate of change of energy with respect to time. Because the derivative of energy with respect to time times delta t is the approximate change in energy over the interval delta t, just like before. Oops, and I realized I just used a partial derivative symbol right here, so this should be total derivative with respect to time. This quantity right here is also giving us an approximation, right, to the total energy flowing through the surface as the boundary of the region omega. Because you're taking the derivative, the rate of change of energy with respect to time, and you're multiplying it by the interval. And these two quantities are, in the limit, going to be equal to one another. So essentially what we have is that for a very small delta t, we have the energy change through the boundary is approximately equal to the energy flux through the surface and as this delta t interval gets smaller and smaller and smaller, total flux at any given instant of time, phi s, through the surface should be exactly equal to the total flow of energy through the boundary. So this equation is essentially setting up that the change in heat energy through the surface S, through the boundary, right, must equal the heat exchange throughout the interior of the region omega. And what this means then is that we can take our integral expression for the heat flux, which was this expression right here, and say that this surface integral has to be directly equal to this volume integral. And we know that if this surface integral is the surface of a piecewise smooth surface and this vector field is nice enough, that this is going to be the same thing from the divergence theorem. As the triple integral over omega of the divergence of k times gradient of u dv which has to be equal to this triple integral. This process right here is sometimes called doing an energy balance. We're just ensuring that the conservation of energy holds inside the region omega. And this is a really neat idea, right? It's that essentially we're connecting mathematics with physics directly when we're doing this process right here. And we've just used the divergence theorem to set up two separate volumetric integrals that have to be equal to one another at any point in time. And we can rewrite this a little bit as the triple integral over omega of the function u times rho times the partial derivative of u with respect to t minus the divergence, where the divergence is the dot product of the gradient operator with this function right here. So it'll be k gradient of u, and this has to be equal to 0. And now the key part in reducing this to what's called the differential form of the heat equation is realizing the following things. This right here is sometimes called the integral form of the heat equation because it's represented as the triple integral. Right? What we want to notice here is that, go back to our picture of the region, this has to be true for our region S, but it also has to be true for any subregion of our region S, any arbitrary subregion. So take, say, for instance, a smaller subregion, S1 here, and then maybe a different subregion, S2 right here. And for any subregion, S1, S2, or any other subregion inside S that's nice enough, this also has to be true. This equation has to hold for any subregion, but in general S star, omega star, that are inside, I'll say, nice enough subregion as well. And this is the key here. The only way that this can happen is if this function vanishes. So this function is equal to 0 inside all of S times omega. And so this is the integral form of the heat equation. The differential form is making the observation that if this equation holds for any subregion inside the original region S omega, this function has to be 0, and therefore u times rho times partial u partial t minus the divergence of k times the gradient of u must be equal to 0. This is sometimes called like I said, the differential form of the heat equation. And there you have it. This equation has to hold in any medium that is geometrically nice enough to apply the divergence theorem and satisfies all of the conditions that allow us to do this. Now remember here that mu and rho and k are all functions. In our derivation, u and rho were functions of position, k was possibly a function of position and a function of time, which in general gives us this equation, but we have an even nicer form for this equation if k is constant, mu is constant, and rho is constant. we can go through and do the following. Well, first off, in general, the divergence of a function times a vector field is going to obey some form of the product rule, which we'll go into a little bit later. But if this is constant, you can very nicely show that mu times rho times du dt is the first term, and then k, the constant term, will come out of the differentiation here and this operation actually has a name. The divergence of the gradient of u for any function u is sometimes called the Laplacian of u. In terms of Cartesian coordinates, this is the second derivative of u with respect to x plus the second derivative of u with respect to y plus the second derivative of u with respect to z. And I can also divide by mu and rho to get that du dt minus k over mu times rho times the Laplacian of u has to be equal to 0. Where I'll introduce one final notation here for what's called the heat diffusivity. And this is the thermal conductivity divided by the heat capacity times the mass density. If we call the value k the thermal diffusivity of the medium, which is going to be k over mu times rho the heat equation in its final general form for constant coefficients will be du dt over or du dt is equal to lowercase k times the Laplacian of u. And so this is probably the more common heat equation that you'll see written out, but it only is really actually nice and valid if each one of these properties or each one of these functions, mu, rho, and k, are constant. So this is a general equation, which is the same equation in any number of dimensions. But for instance, the general 3D equation is a partial differential equation. 3D form is saying that the partial derivative of u with respect to time in Cartesian, and I'll do it in Cartesian coordinates as well. This is going to be k times the second derivative of u with respect to x, the second derivative of u with respect to y, is the second derivative of u with respect to z. In 2D, this is saying that du dt is equal to k times just the second derivative of u with respect to x plus the second derivative of u with respect to y And in 1D, it reduces even further, saying that the derivative of temperature with respect to time is equal to K times the second derivative of U with respect to the x coordinate. So this is really neat what we've done here. And we will be getting into a little bit later in the course a very, very amazing method of actually solving this, and I'll go over examples of how to do it in 1D and 2D, but we'll actually also, the methods that we go over, learn how to do it in 3D as well. Now, I want to give you a caveat here. This is not going to be a general solution for any general domain, but it'll be for domains on which this differential equation is separable. So more on that a little bit later. But what I want to do is show a direct example of what the solution, the exact mathematical solution to the heat equation looks like in 2D. Or a relatively simple initial distribution of temperature. And so this is a plot of a 2D initial temperature distribution. Specifically, the temperature in the blue region is 0, and the temperature in the red region here is 1. On the right-hand side, I just have a density plot of the temperature showing the density. On the left-hand side, I have a graph plot, so a graph of this function of two variables. And you can see very clearly that it's 0 on outside of this little square, and its temperature is 1 here. And what I'm going to do is show the exact mathematical solution to this heat equation. I shouldn't say exact, it's the approximate solution using Fourier series, which we're going to be getting into as our next topic. Specifically, it's the sum of the first 100 terms in the Fourier series, but this actually converges to the exact solution in the limit as n, or the number of terms in the Fourier series, goes to infinity, which we'll show in the next couple weeks. And you see very clearly, though, that this is doing all of the things that we expect to do. Specifically, the heat is flowing in the direction of the negative gradient. The gradient of this function is always pointing uphill, the direction of fastest increasing direction of the function, and the temperature is flowing away. So it's flowing out, and temperature is decreasing in a very physical, intuitive way, all the way until we get to the final time of t equals 10, which is when I ended the simulation. But this is really neat, and something that we'll be getting into in the next couple weeks of the course. So the heat equation doesn't just govern heat, it actually governs a wide variety of phenomena in physics. Everything from diffusion to, you can couple it with reaction diffusion equations and all sorts of very, very interesting applications. But I think this is a good summary and a good spot to end the lecture. Thank you very much for tuning in. I hope you had a fantastic day and that you learned something.